Hi guys. So since we've been able to cover combinational logic circuits, we're going to look at a very important application of that, which is decoders. So for the next couple of videos, we'll look at defining decoders, why we need them, a handful of applications, and then we'll wrap it up with the most common example, which is the 7-segment display. All right. So let's get to work. What's the decoder and why do we need them? A decoder is a digital circuit. Okay, so that's the first thing to establish. It's a digital circuit designed to detect the presence of a particular input of a particular digital state. So these are three important things we'll see from when handling decoders. First of all, they're a digital circuits, a digital logic circuits, as we've been dealing with throughout this course. Designed to detect, so that means decoders are able to help us know when a particular digital state is happening. All right. The general function of a decoder is to activate one or more circuit outputs upon detection of a state. So the peculiar thing that happens is that usually for all the circuits we've been handling before, let me just draw an example one for now. Okay, so let's say this is just a random circuits. So, all right, all the circuits we've been dealing with so far have all had one output. So even though this is ABC, you only have to deal with one output line, meaning that for the case 010 and the case 111, the outputs is all of them are going to be indicated on this line, on this output line, meaning that we have only one way of receiving our outputs. So we can only tell when this is high or low, but we're not able to tell from our output line the situation that's going on in the back end. So I like you to think of this as a really funny reason as to why we sort of need decoders. The reason is kind of hard to understand what babies are going through, right? So let's see if we can draw an angry baby that's crying. Okay. The reason it's kind of difficult to understand what babies are going through is that they have only one sort of output, which is them crying. Okay. So a baby crying could mean that they're hungry. Okay. Thirsty. What else could that mean? It means they could be hungry, thirsty, angry, or pressed. So these are four particular combinations of input states that could all four of them could happen in any combination for the baby. And the only way we're going to be able to know anyone is happening is that the baby is going to be crying. So imagine, if you will, the perfect baby. Okay. So this is a perfect baby, really happy. And this baby has 4 mouths. 1, 2, 3, 4. We'll label this mouth H, mouth T, mouth A, and mouth P. So now when our baby with 4 mouths cries with mouth T, we're able to tell, oh, my baby is thirsty. Whereas for the case where we had only one output line, we're only able to see our baby crying and not really know the particular situation behind that. So that's the advantage we encounter when dealing with decoders. Having multiple output lines for each state make it easy for us to tell when such and such is going on. So the general function of a decoder is to activate one or more circuit outputs upon the detection of a state. The general function of our perfect multiple mouth baby is to let us know what particular input is causing mouth angry to cry. Okay, so it sort of makes handling logic and dealing with logic much easier. Okay, so now we're going to look at a very important concept when handling decoders. All right, and that's the idea behind active high and active low logic. So what does this mean? To explain this, I'm going to have to draw 2 particular gates. Okay, the first one is this is going to be the AND gates, and this is going to be a NAND gate, just so we can get ourselves to understand what really is going on behind the scenes. Okay, so let's see. Let's call this AB output Y and CD output X. Okay, this is the NOT AND gate, and this is the AND gate. All right. So what's going on? Let's draw the truth table for both of these cases. If you have A, B, and output Y, so let's get 0, 0, 0, 1, 1, 0, and 1, 1. our output Y is going to be low for every case except when both our inputs are high. All right. The opposite is the case when handling this. You have C, D, and output X. 0, 0, 0, 1, 1, 0, 1, 1. Okay. So our output is going to be high except on the case when 1 equals 0. So what does this mean for us as we're handling digital electronics? It means that my AND gate is able to tell me that out of the 4 combinations of the AND, when I have both of my inputs high, then my output is going to be equally high too. Okay, which is why you will see sometimes that the AND and NAND gates are the simplest decoders. All right, so the 2 inputs simple decoders. So look at it. Out of the 4 possible outputs, 1, 2, and 3 are low, and this is high only when these two are activated. Meaning that I'm able to say that my AND circuit, okay, is normally low. Okay, so what does this mean? When my inputs are low, my output is going to be low. If I toggle one input, my output is still going to stay low. If I toggle both of them, okay, so that's 1, 0, my output is going to stay low. So only in the very unique case when both my inputs are high, 1, 1, I'm going to have an output high. So you can see that this is the active high combination. Okay. Meaning that in order for my outputs Y to be active, it's going to need a 1, a digital 1. All right. So normally low is paired with active high. Okay. Normally my circuit will be low, and applying the signal to both of my inputs is going to give me a high value on my output. You can see that almost the exact opposite is in the case when dealing with the NAND gates. All right. Out of the 4 cases, in 3 of them, my circuit is high rather. So this is a high value, this is a high value, this is a high value. And in the case where both of my inputs are high, for the case CD, I'm going to have my output being drawn low. So this is why you say the NAND gate is active low. Okay. So NAND is normally high. Okay. Meaning is active low. Because the natural state of my circuit is to be high. And for it to be active, the 1 will have to change to a 0. Okay. If none of my inputs were on, if my circuit was deactivated, my output would be high. For me to indicate that both of my inputs are in use, my circuit have to drop to a 0. So it's the same thing here. So active high and active low really also work with the normally high or normally low. If my circuit is normally low, then I'm going to need an active high configuration. That's what we have when dealing with AND. If my circuit is normally high, then I'm going to need an active low configuration. So that's a very crucial thing we have to consider when dealing with logic circuits. All right. So now see if we can solve a handful of single gate problems when handling decoders. So these are single gate decoders. All right. So they are much more simplified forms of decoders where what will usually be complex, we're going to take a snapshot of it and have only one. All right. Recall that decoders are able to transform n input lines to 2 raised to n output lines. Okay. So if I have 2 inputs on my decoder, I'm going to be able to get a maximum of 4 output lines. All right. So seeing that we have 4 inputs here, this is a single gate decoder because it takes just one scenario out of all of that. So we're going to solve for these and see the scenarios that cause this. Exactly. Okay. So handling question 1. Determine the logic level of the outputs and the input code that activates the following decoders. So a general rule of thumb is that once you see an AND gate, it is wonderful to assume that you're dealing with an active low logic. Okay? Active low. So that's the general rule of thumb. Remember what we just covered the previous section. Well, I'm dealing with active load. That means my circuit is normally high. And I need a logic 0 to indicate that this input is being met. Okay? So also write the Boolean expressions for each. So starting from the most significant, so that's DT. we can see that D2 is being negated. So as not D2, not D1, and D0 is equal to not Y. So writing the binary equivalence for this is to be, okay, let me just flip this. Not Y is 0, 0, 1. So that's all that happens when you're dealing with single gate decoders, all right? You look at the gates. Am I dealing with an AND gate or an OR gate? And am I dealing with an AND gate or a NAND gate? All right. So once I'm able to detect the gates, I can then go on to say which input configuration is responsible for this. So solving the next question. So here we had dealt with 3. Now we're going to deal with 2. All right. The first thing we're going to have to do, what gates is holding this decoder together? This is an AND gate. So I'm going to say that this is active high logic. Okay. Remember what we said, an AND gate means you need a high signal to raise a high signal in the case that both inputs are activated, meaning is normally low. So active high means normally low. Active low means normally high. All right. So looking at this, we start from the most significant bits as D3. So D3 is regular. D2 is okay. D3 is regular. D2 is negated. D1 stays the same, and D0 is negated. And this is as our output Y. Okay. To find the binary, so this is the Boolean expression. They were meant to determine the input code. So the input code for this would be 101010, and that's all there is to decoders. All right. So let's do the last one just to make sure our hands are mighty sharp. This is a NAND gate, so I'm going to say that this is active low. All right. I'm going to start from the most significant bits, D3. So that's D3, not D2 because of the negation gates. All right, this is an inverter. Not D2, not D1, D0 is going to equal not Y. All right. So not Y is going to be 1001. Okay. So it's important to note when dealing with normally low, dealing with NAND gates, that's active low, that your output here is going to be not Y. All right. Since you're dealing with the active low configuration. But if I'm dealing with active high, that's my AND gate, my output is going to be Y. So that's all there is in being introduced to decoding decoder circuits. In the next videos, we'll solve more problems looking at 2-line to 4-line, 3-line to 8-line, and other types of decoders so that we can get more familiar with them. Thanks for watching.